Hi everyone. Thanks for coming today. So today we wanted to talk about the new product that we are working on, which is the ingestion platform. And a couple of us are going to be speaking today. So I'll be giving an overview of the platform. And then we have Vlad, who would talk about some specific applications that might be of use to you. So just show of hands, how many of you have been here before to any of our meetups? Is this your first meetup here? Okay. And any of you basically dealing with ingestion problems in your workplace? Okay. What kind of?
We are using Hive as far as ingestion is concerned into the data warehouse.
Okay.
So we are facing problems as far as the performance is concerned.
Mm-hmm. Okay. You mean to get data into your warehouse?
Right.
Okay. All right. Okay. Yeah. So we'll talk some about performance. Actually, the core of this talk is focused around fault tolerance and scalability. So that's critical. Okay, so
Pramod, there's a question if we could cover or talk about scoop.
Sure, we can make,
Maybe comment later.
Yeah, we can comment on it. Okay, so what's big data ingestion, right? Or ingestion on Hadoop. So one of the main challenges is nowadays you have a lot of data that's coming in. Sometimes it's streaming in, and and you have to be able to ingest this data and basically be able to do it quickly enough so that you're ready for the new data that's going to keep on coming. So your ingestion solution should be able to scale with the data. Right? You need to be able to support a variety of sources. If you're starting from scratch, you may choose message queues like Kafka or other ways of ingesting data. But if you already have traditional setups and you're migrating, you may have data that's already in warehouses or databases or even in files. And big data and Hadoop actually give us an opportunity to do more than just plain ingestion. You can actually do some cleansing, filtering, enrichment, and do some transformations on the data as it's coming in. And the next 2 points are very important. Suppose you're basically running an ingestion application or ingestion pipeline, and it's been running for a while, and there are failures in your cluster or in your system. The application needs to be able to recover and not have to like restart or reprocess, re-ingest everything from the beginning. So it needs to be able to do that, and it needs to be able to do that automatically. And when this happens, it should be able to recover without any data loss or duplication. And you should have the flexibility to be able to create different kinds of pipelines because there's no one size fits all, right? So what's our solution? So our solution is actually a platform that's actually configurable. So the user can put together their own ingestion pipelines using a set of building blocks. We call them operators. We support a variety of sources and sinks out of the box. A few of them are listed. We support filters and transformations again. The system comes with those. But it's extensible. You can add your own to the system. If you have any business logic that's specific to your problem, you can add it as well. And it scales with data, so it can scale dynamically. And underneath, it uses the Apache Apex stream processing platform. And it's a very scalable and fault-tolerant system. And each stage of your ingestion processing can scale independently. Okay, and same with failures. It maintains your data integrity. There is no loss of data, when you have hardware failures. Okay. So how does the application stack look like? So at the this whole platform runs on top of Hadoop. So you need Hadoop. That's the lowest thing in the stack. You could be running on-prem, on cloud, or with virtual machines. That's fine. And any major Hadoop distribution works. And on top of it, you have Apache Apex, which is the runtime engine. And on top of Apex, we have a bunch of building blocks or operators. And you would construct your own ingestion pipelines with these operators. And these ingestion pipelines are actually running on the Hadoop cluster. Okay.
So operators is basically kind of different transformations?
Yes, they would be transformations or connectors or any other kind of processing that you are trying to do.
Like filter is one type of transformation. Yes. We have to select that thing.
Yes, that's correct.
And we'll build the pipeline.
Yes, so this is our application designer. So we provide a bunch of these building blocks or operators that you see on the left side. And you can add to those as well. And you basically drag and drop and build your pipelines. So this is a sample pipeline that's reading data from Kafka, JSON data that's parsing the data, doing dedupes, and then applying transformations and saving the data to HDFS. Now you could switch out the HDFS and put in a JDBC and write it to some database. So later on, Vlad will be demoing this particular application. And you can configure it right in this designer and even launch from here. And it'll basically launch on your Hadoop cluster. Okay. So, I want to talk a little bit about Apex, which is the underlying.
Sorry, quick question on the slide you had before. You mentioned about like if you put a JDBC output at the back there, then do I also need a separate operator to go to write to some database or?
Yes, so you'll use basically a JDBC output operator or like a MySQL Postgres operator. That would be the operator would be the one that will be writing to your database.
Right. Oh, sorry, they just handed me this microphone. So do you have output connectors for databases already defined or just JDBC?
Yes.
Or?
Yes, so we do have. So if you look at it, we have a generic JDBC. So and as an example, we have, for example, Postgres input, which is the inverse of that, right, at the input side. So essentially, you can take this JDBC output and specify a driver, or you can drag and drop a pre-existing one. So that's already configured with the driver. So it gives you more flexibility. So
Pramod, there are questions online. What events can lead to failures requiring re-ingestion in your experience?
Typically, right, if you're ingesting a lot of data and these apps are running continuously, you may have node failures in your cluster. So that's primarily the chief cause. Sometimes you may have other things going on in your system, other processes that may interfere and cause some other failures. But it's mainly node failures.
Thanks. One more question. What are the operators that can be used for ETL?
So we provide a transform operator, which basically using expressions, simple expression language, you can define different types of transformations. We are filtering. So these are some of the things that are dedupe. So these are some of the things that we provide out of the box. So right now this is a new product, and this is right now in beta, and we plan to add more of these so that when it comes out, you'll have a good set of these out of the box. And if you wanted to, if you needed something that's not in the list that we provide, then you can implement it. You'll have to implement it in Java, but there's a well-defined API to do that, and it can be added to the list on the left side. Okay.
Thanks. One last question, and then I'll hold on.
Okay.
Does it support Avro?
We right now we don't have it in this list here, but we do plan to add an Avro support. So just as an FI, there is Avro support in Apache Apex already, and we're planning to have it here in the studio as well. Okay. So what's Apex? So Apex is a real-time in-memory distributed processing system that basically runs on top of Hadoop and lets you basically run. You can build any type of application, and basically with a set of operators, and then they can take the full advantage of the computing resources that are available in your cluster. So as opposed to the traditional Hadoop applications, which are more batch-based and which probably use files as the intermediate mechanism, this is purely in-memory and over the network. So it can process your data with really fast, with minimum latencies. And basically, it supports. Its programming model is very simple, and you can basically write any type of custom logic in Java. And it provides a simple API to be able to transfer data between multiple stages and create a pretty elaborate and big application. It also lets you maintain state, which is critical for doing any type of analytics. And the other two important features are it's highly scalable. So each of your operators can actually can run as multiple processes, so they can parallelly ingest data from your sources and process data in a parallel fashion as well. And they can do so. This parallelism can be statically defined or it can be dynamic. So if your load increases, more of these will be deployed, and as the load reduces, the system will scale back the resources. And the other important aspect is fault tolerance. So as I mentioned, if any of the nodes in your Hadoop cluster go down, the system can figure out the pieces of the application that have gone down, recover, restore them, and handle it such a way that none of your data is lost, and also it maintains end-to-end exactly one. So if you're writing to a database, no data will be duplicated in your database as well. And there are a whole bunch of operability tools that are available, so that they give you so that you can actually see what's going on with your application.
Question on this slide, can I define my in-memory size before processing?
Yeah, you can. So you can actually define the in-memory size for each of your stages.
And fault tolerance that you are talking, that comes with the Hadoop features, right?
No, so Hadoop, so Hadoop 2.0 basically is composed of two components, Yarn and HDFS. And Yarn is merely a resource manager. And HDFS is a file system that of course, when you save some files, it gives you redundancy. But this is all in-memory compute, right? So there is nothing provided. There's no default fault tolerance available. That's sweet. Yeah.
The latency in comparison to Storm, do you have any benchmarks?
We do have on our website. The latency is much smaller for us because we don't rely on acknowledgements on a single tuple basis, which Storm typically relies on.
Okay, and when you said about the scaling, in Storm you have to define it before the process starts, before the first tuple is read. And you said that you guys do it pretty, you guys scale it automatically. Is there a way how you guys do it?
Yeah. So good question. So we support two modes. One is you can specify the scaling factors at the beginning. The other way is you can specify in terms of SLAs. So you can say that each of my compute unit can handle a throughput of, let's say, n,000 events per second or something like that, right? So as soon as the threshold is breached, then the system will create more of those automatically. Similarly, when the load comes down, it will give back the resources. So this could be, for example, even latency. So you can say, as soon as my latency of a compute unit is crossing 5 milliseconds, go ahead and create more, right? So you just can parameterize and specify them as parameters, and the system will scale accordingly.
Okay, the online questions. One from Satyan Nair. Can you give implementation architecture use cases sometime during this session?
Sure, yeah. So the second part of the session is actually implementation pipelines. That's
Okay. And Satyan is specifically looking for implementation that is based on cloud using PaaS, using platform as a service.
So you can build cloud solutions on top of it. In fact, we have a customer who's doing that. We currently do not provide cloud service, but definitely you could build on top of this.
The next question is, do you have any metadata management facility built in?
No.
Next question from Vinod Jaykumar is there an option to do in-memory analytics without persisting data in HDFS?
Yes, so with this you do in-memory analytics without persisting data in HDFS.
Okay, and the last question, from Sufyan Asad, can this resource taking and retrieving model be extended to Amazon AWS so that it would automatically take most pod instances and give them up when work is done?
Yes, so there's two levels there, right? So you have to basically have more resources available for Hadoop, and then we will have automatically more processing resources available for the applications. So at some sort of a triggering, so right now what happens is the application will scale up to the amount of resources available in Hadoop, right? And not beyond that. So you need to build some sort of a triggering mechanism where you can request AWS to give you more nodes for Hadoop.
One more question, couple more questions. One from Ram R. Can you add custom operators other than default operators supported with Apex?
Yes, you can.
And one last from Shiva. Do you have any demo today?
Yes, we do. Okay, those are easy. All right, so this is the this is the platform stack of how of applications on Apex. It's very similar to the one you saw earlier. So it basically runs on top of Hadoop, and it comes with a streaming runtime engine that ensures the fault tolerance and scalability. And on top of it, you have your pipelines, and also there are a big library of operators that are available for you to use. So some folks asked, are there other operators that we can add? You can add, sure you can. And we also provide a library of those. And there are a bunch of tools on top that provide bunch of UI tools on top that basically provide you more ease of access or more deep monitoring, and the the pipeline building functionality that you saw before. So there are 3 tools that DataTorrent provides. So one is a management console where you can see what's happening with your pipeline as it's running, each stage, how it's performing, and if there are any failure and recovery events, you can see them as well. You can even record data as it's flowing through the different stages. You can add visualizations. You can do visualizations on metrics that you define, or you can even have visualizations at a system level, or even for you can even send real-time data out and visualize that while you're ingesting. And of course, the design studio that you saw, where you can actually build these pipelines.
So there's a question on this slide. What is the difference between Malhar and Apex?
So Malhar is one sub-project under Apex. Apex project has 2 pieces. One is an engine, that's a runtime engine, and then Malhar is a library of operators. So the application development model on top of Apex is it's a direct acyclic graph. So you take individual components or the building blocks of your application and then connect them together. And each component implements a portion of your logic. So for example, in this case, the first operator could be bringing data from an external system like Kafka or JDBC. The second one could be doing some parsing. The third stage could be doing some filtering and enrichment, and then the final stages could be doing some other extra processing, and the last stage could be writing data out to another data store. And the data is flowing continuously, and you can process this data at an event by event basis. As soon as the event is sent by a previous stage, it's available. It basically we basically make sure that it gets to the next stage as soon as possible. So there is no artificial batching or delays added by the platform.
One question here from Vinod Jaikumar. Can I calculate metrics on data ingested via streaming? For example, uniqueness, cataloging, metadata, etc.
You can. There is a feature called Autometrics. So in your operators, you can basically calculate these and just mark them as autometrics, and they would automatically be collected, and they would be aggregated as well based on what type of aggregations you want. So you can have historical aggregations of these metrics, and then they are available for you to visualize or available to you to fetch via REST APIs. Okay, any other questions? Okay, so here's a slide showing the different scalability features that are available. So here you're seeing, in the first picture, you're seeing a 3-stage pipeline, or sorry, a 4-stage pipeline, and so you're seeing stage 2 and stage 3, which are marked 1 and 2 because the numbering started from 0. So they are being scaled into multiple processes, right? And they're being scaled independently. So for example, stage 0 may be fetching data from somewhere, and it's probably lightweight. It's not doing a lot of processing. But on the next stage, you may be doing a whole lot of processing, right? And it might be more CPU intensive. So you may want to have actually more than one of these processes running parallelly, and the data from the first stage is divided, right? So now you can basically process the data much faster than if you're doing it on a single process. And then picture below shows you parallel pipelines. So if you are doing a bunch of operations on the same piece of data and you're not really doing any aggregations that require some sort of a stickiness within the data, then you can actually move the data much faster by moving the same pieces of data through multiple stages of processing without any shuffles involved in between. And then at the end, when you're unifying the results, those things can also be done in multiple stages of unification, like that picture is showing you, where you have these multiple partitions producing, they're doing some computations and producing their results, and the results are all being merged, right? So think of it like, let's say your operator is doing a sum, right? Earlier it was, let's say if it was one instance, it was getting, let's say 10,000 pieces of data. It was calculating a sum per minute, and it was per second, and it's calculating the sum. Now, if you divide it into 4 partitions or four operators, each of them, let's say, get equally, and they get 2,500 pieces of data. So they now each have calculated partial sums, and those results have to be merged. So those will be merged by these unifiers. Okay. Any questions so far?
I'm thinking more in terms of latency.
Okay.
I'm thinking more about latency
Okay.
when it happens, across parallel operators, because each one is operating, atomically. So if there's latency at the per window level, how do you take care of it? Because it would still be the same. I think you guys also use tuples, right? So at a tuple level. So if say in the first example 1A is causing a delay, and the unifier will wait for the 1A operation to complete and then take the 1A, 1B, 1C together for the next window, or it'll just go ahead?
Yeah, it will. There is the synchronization does happen on window boundaries. So if one of your operator is delaying, then it would basically affect the downstream. Yes, but if you're in parallel mode, that won't happen. If you just go parallel mode all the way to the output, then each of them will not get affected by the others. So in fact, we've had a customer who's doing pretty critical processing. So they're actually processing credit card transactions in the loop. When you swipe the card, they need to send a response back. And they need to do it within like a fraction of a millisecond, actually. So they cannot be affected by even small latency, some small latency effects, right? Like because of garbage collection or any other thing that's happening. So they run parallel pipelines, and most of the time, all of them are within the latency boundary. But let's say if there's some event and one of them goes outside, has more latency, that doesn't affect them because one of the other two will respond. And as soon as the first one responds, they're fine. Okay.
Pramod, there's a pretty deep question online from Vinod Jayakumar. Is there a specific replication factor suggested using Apex? For example, name node failsafe for HDFS or in-memory application? How do you not lose data?
Yeah, so we use a pretty innovative approach. We don't need to replicate data. So what happens is we maintain a buffer along with every operator, and the buffer maintains the data till it's no longer needed by the downstream. So if an operator dies, basically it will restart from a previous checkpoint, which I'll cover in fault tolerance, and it will pull the data back from the upstream and do any recomputations that it needs to do from the checkpoint. So that way, and if the upstream dies, then it'll pull it back from its upstream, and it'll recompute. And then we don't need to store a whole bunch of data in the buffer either, because these operators are checkpointing, and once they're moving forward, we can just discard the old data. So at any point of time, there's only the transient data between checkpoints that's in memory. Okay, any other? Okay. So the next important aspect is fault tolerance. So you have this pretty, let's say, big DAG that's running on your distributedly on your cluster, and there is a node failure, and that takes down some operators, right? We cannot have the application go down or produce wrong results. So what happens is the engine automatically figures out what processing elements have gone down, and it will recover those pieces and other pieces that are affected because of those. So to do that, to be able to do that and not take a long time in doing that, what happens is every operator is periodically checkpointing its state, right? State is actually not data. State is any computations that it's performing. So for example, if you're performing things like aggregates, counts, sums, so those kinds of things. And this state is persisted and saved into HDFS for every operator. It happens in a distributed fashion, so there are no bottlenecks. And then when there's a failure, the operators, the affected operators are restarted from their previous checkpoint, and then they replay a small amount of data. So usually the checkpoint interval is 30 seconds by default if you don't change it. That means worst case, if an operator fails, it's going back 30 seconds back, and then it's processing. And if you have some processing slack built into your system, then it'll catch up, right? So because of this, because of the buffering and the checkpointing together, we actually don't have to restart the entire pipeline. We only need to be, we'll only recover the parts that are affected, right? And all this happens automatically, and all this happens without requiring the user to do anything special, okay? And also, so when this happens, right? So there is a small amount of replay, right? Because each operator is going back, worst case 30 seconds, and then reprocessing a certain amount of data, right? So this is called at least once. Sometimes in the industry, sometimes when you read literature, you may see the word exactly once. So people some people call it exactly once, but it's actually not exactly once, at least once, because if you have an operator that's writing data outside and it's reprocessing some amount of data, it can end up writing duplicates, right? So we need to protect against that. First of all, this mechanism ensures that you don't lose any data, but you need to do additional work to basically make sure at the end, if you're writing to an output store, you don't have duplicates, right? So that is called end-to-end exactly once. And we actually, so our platform and our operators, they basically work together to basically ensure end-to-end exactly once. And I'll give you a couple of examples. So let's say you're writing to, let's say you have an operator that's writing to files in HDFS, right? So data is coming in and it's writing files, right? And periodically the operator is checkpointing its state. So let's say a checkpoint happens here, a checkpoint happens here. So at these checkpoints, what's happening is it's just storing the file offset. So the only thing it's has in memory is an offset, it's a few bytes. So that's being persisted somewhere in HDFS. And this here, the data is being written normally, right? Let's say some more data comes in, there's another checkpoint, new offset gets written. Okay? You're writing, so you're continuing to write data to the file, and suddenly there's a failure, right? So now your operator has gone down, and then the platform basically figures out that your operator has gone down. It will restart the operator. It will restart it from the last checkpoint, from this point here, right? So, however, the file has some extra data, right? So as soon as the operator is restarted to the checkpoint, it will automatically have this offset in memory because the platform will restore this offset. So when it starts up, it will truncate the file back to that length. Okay? So this is how the platform and the operator work together. So it will truncate the file back, and then when the data comes back, the replay data comes back, it just continues writing, right? So you have not lost any data, you haven't duplicated any data. Okay? So this is very important with ingestion because data loss is the primary problem, right?
Okay, there are a couple of questions online. First is, how is streaming data handled for multi-tenant Hadoop architecture?
So,
From Vinod.
Yeah. So, I mean, it will depend totally on your operators. Let's say if you're trying to mix multiple tenants data in a single application, or if you are actually using different applications for different tenants. Because we give you the complete control in your operators to actually process data in any way you like. So if you have some distinguishing factor in your data and your operators use that to separate the data in some logical fashion, that's totally fine.
Okay. No, the same application with different tenant.
Right. So
two different instances of the same application.
Yeah. So each application will run independently, and so the data won't mix. So they will, even if they are, they will basically be sending data to their own operators, and you could have them run as two different accounts in secure mode. So.
Okay. The next question is, does the at least one model make sure that the aggregates do not have double counted data?
Yeah, so basically they won't. So basically what happens is, so when there's a failure, so the operator basically recovers from its previous image. Its downstream operators are also recovering from that same point. So all of them are kind of like rewinded, right? So they're like deja vu. So they are reprocessing some amount of data. But the last operator, right, that is actually writing to the external store needs to do something special because it may have already materialized the data, right? So here I'm showing you examples, like if you do that, how can you still ensure that there are no duplicates? So this is the files case. Next we'll go to the database case. So there is a little bit of amount of work that needs to be done by the operators, but platform helps it to still maintain it end-to-end exactly once.
Another question from Sufyan Asad is, if multiple replays happen for some reason and operator has to replay the data, can this lead to buffers ingesting live data filling up? And how tolerant is the application against such scenario?
Yeah, so if you have continuous failures, or if for example there is some other problems and we are not able to get the containers quickly, yes, the buffers will fill, but there is a relief system built in. So there is spooling of buffer server data to disk. So that's a mechanism as well, but it can be turned on or off, and then there's that basically introduces back pressure, and it goes all the way up to the first operator.
Okay.
Yes.
And one last question. If you have, I think it relates to two instances of the same app. What if you're writing to the same file?
Yeah, you shouldn't be doing that. Of course, it doesn't protect you from everything. Just like a programming language doesn't protect you from making your own mistakes. So.
One more question from Vinod. What if the ingestion is via an external data feed REST API? Will the failure cause a second call to resume the ingestion?
Could you repeat that question?
What if ingestion is via an external data feed REST API, like RSS? Will the failure cause second call to resume the ingestion?
So, yeah, I mean, if I'm understanding the question correctly, you're saying that, let's say your input operator is actually bringing data from using a REST API from an external system. What happens if there's a failure of the input itself? That's just like any other failure. The input operator will automatically resume from its previous checkpoint, and it will pull data. Of course, so there needs to be some memory in the external system so that the input operator can go back and say, oh, can you give me this old data again, right? Suppose such a memory is not available, then the input operator can be instrumented so that it can save this data for some time in HDFS so that it's available for a replay. Of course, in those cases, you can't truly guarantee data loss 100%, because there could be some time where you actually fetch the data from the external system and while you are saving it, there's a failure. So there's like a really, really small percentage chance where you can lose the data. But of course, if the external system supports some sort of acknowledgements where it gives you the data, but till you acknowledge back, it doesn't delete the data, then you're still okay. Right? Okay. So let's see what happens when we are writing to databases, right? How do we guarantee exactly once in case of failures? So what happens is, let's say this is a table where we are writing some data. So just some simple table. And then what we do is we also maintain a meta table in the database where we basically write the last processed window ID. So window is just a periodic boundary bit of your data. So basically by default it's set 500 milliseconds apart. So for example, let's say you processed let's say checkpoint happened somewhere here, and then you process data till window ID. So that data, so this meta table, that particular window ID is written, and it's written in a transactional way along with your data, so that it's basically either atomically committed with your data or not. So in every window, what happens is the data and the window ID are written in the same transaction. So let's say you wrote you're writing some data and then there was a failure, right? So what happens is all the data in this partial window would never appear in your tables because that transaction was never committed, right? And then the last particular window that was fully processed is in this meta table. So what happens is when the operator, the platform sees the operator is dead, it will restart it from the checkpoint and it will send it the data again. But this time, the operator will not write the data into the database till it reaches this particular window. So it will ignore all those windows, and it will start writing data again when it crosses that window boundary WN. And then when it finishes the new window, then it updates the meta table again. So this way, we basically ensure that in case of databases, we're not writing data again. So the reason we have to do this versus files is because there is no specific order, right? When you're storing these data in the database in the rows, they can be in any order. Okay. So then back to our ingestion solution. So what does it contain? So it's basically an application package. So in our world, application package is basically a collection of applications. So we provide an application package with a whole bunch of operators that are ready to use for geared towards ingestion. Some of them are listed here. You already saw them in the slides as well. And then it also comes with a couple of pre-built pipelines. So we have these example pipelines. One of them is Kafka to HDFS with a deduper, or another one is HDFS sync if you're trying to sync data between two HDFS clusters, or from S3 to HDFS. And it's currently in beta. And if you're interested, please contact this email address, info@datatorrent.com. And we would love to work with you and see if this solution solves your needs. Okay. And a few resources about Apex and DataTorrent. And any final questions?
Suppose there's an operator and I want to, like, suppose there are like 4 operators and 1, 2, 3, 4, where 4th is the final output operator, and I want to make changes to my 3rd operator, logic changes. Is it possible for me to just do it in runtime without really, affecting the entire program?
It's a good question. So there is a way to do that today. However, you cannot just make the change and upload it onto the running application. You can take down the running application and you can restart the new application starting from the state of the previous application. So you can make it continue from the previous state, right? However, that means that the new operator logic change that you make has to be compatible. It cannot be like something totally different. So for example, if your operator number 3 had a particular state, right? Let's say it was a map of strings to some integers. The new one cannot be a map of string to longs, right? You can fix your bugs and things like that, but the state has to be compatible, because what will happen is when we restart from the previous state, we'll take the old state and load it into your new operator.
Can I, so in my use case, it's more about writing to an end database, and I want to add more columns to write. Can I do that? In this case, it's
Yes.
not a manipulation, but
so what we can do is, so in that case, your input operator, where are you getting your input data from? Can I ask? Kafka or somewhere?
Yeah.
Kafka, okay. So the input operator has the offset, the last committed fully processed offset, right? So when you restart with this new thing, right, it will basically start from that last offset, right? And it will continue getting data from there, and then your new code. So that means you probably won't have any state in the intermediate operators. So that'll probably work.
Okay, so your operators are simple consumers.
They are actually, so our Kafka operators, they actually don't know the full details. They're simple. They basically implement a lot of the offset recovery and all that, right? Yeah, so I think that's simple consumers, yeah. They also are dynamically scalable, so if you have, it'll detect the number of partitions on the Kafka side, and they'll create number and read parallelly. And even if you change the partitions of topics while the application is running, it will reconfigure itself. So on the Apex.
There's a question online. Does your solution provide backup and other management features out of the box, or do they have to be manually implemented by the customer? From Sufyan Asad.
Can we find out what specific backup they're looking for? So if you're trying to do things like replications, those could be done with operators, and we have an app as well for doing replications between clusters. Okay.
Last one. So if it's a streaming data and I want to do calculations across the window,
okay.
So if I want to do the calculations across the windows and not pertaining to per window calculation, is that possible now?
It is. It's been always possible, because you don't have to. For us, window is just a periodic event to your operator to do something. Your operator can maintain state across windows. So actually, when we say state, we mean that you're keeping something across for a long time. If you're doing something within a window and you're kind of deleting it in another window, it's actually stateless for us, because we don't have to save anything, right? Because checkpoints are happening at window boundaries. Okay. All right. Thank you. Okay.
Suppose there are 2 pipelines. Can I prioritize 2 pipelines? Means this pipeline would be executed fast than this pipeline.
So we basically, so the one thing we did is we don't implement our own queues or scheduling or anything like that. So we're relying on Yarn. So if whatever priorities you have given to the Yarn queues, and and you can specify a queue when you're launching the application. They'll just follow that.
Thanks.
Okay. Right. Thanks.